suppose we take a matrix with the first row as 2 and 0, and second row as 0 and 3. Now multiply this with a vector 1 and 1, which looks like this vector. After multiplication, the output vector becomes 2 and 3. This means the original vector 1 and 1 got stretched, and it was also rotated a bit. In short, it transforms your input vector into another vector, which we call output vector. That's when ideas like rank, nullity, null space, and column space start popping up. Okay, let us start with column space. In most places, column space is simply defined as the span of its column vectors. And that's it, which often leaves us confused, wondering what it even means. So here's the most basic way to think about it. Where can this matrix take me? Okay, consider this matrix A. Now let us take any random input vector, say 2, 5, which will lie somewhere here. When you multiply this vector with this matrix, you get the result as 12, 36, which we can also rewrite as 12 times 1, 3, and it will lie somewhere here. Now let us take any random input vector, say -1, 2, which will lie somewhere here. When you multiply this vector with this matrix, you get the result as 3, 9, which we can also rewrite as 3 times 1, 3, and it will also lie somewhere here. This way, if we take any vector a, b on this plane, we will get this on multiplication with this matrix. Now if we take a plus 2 times b as common, we get a plus 2 times b times 1, 3. So what do you observe? No matter what input vector we choose, whether it's 2, 5, or -1, 2, or anything else like a, b, the output always ends up as some multiple of the vector 1, 3. That's interesting. In other words, this matrix can only take us along one specific line in space, the line spanned by the vector 1, 3. That line is what we call the column space of this matrix. It's the set of all possible outputs you can get by multiplying this matrix with any input vector. Check closely. The second column is just 2 times the first one, or it is linearly dependent upon the first column. That means both columns lie along the same line. So no matter what combination of them you take, you'll always get a point on that line. A matrix is made of columns, like if we have a matrix A as A, B, C, and D, and if we multiply it with an input vector x and y, then we get this as the result, right? We can also split and rewrite it like this. So, taking x as common, we get this as x times a, c, plus y times b, d. So, it is clear that the output vector is nothing but the set of all linear combinations of the columns of the matrix A. That's it. Now, this definition will make much more sense. Column space is the span of its column vectors, because when you multiply a matrix by any input vector, all you're really doing is mixing its columns in different proportions. So, in our case, the column space of this matrix A is the span of the vector 1, 3, which we write like this. Now consider this matrix. We can represent its columns like this, which will look like these on a graph. These are independent columns, which means they're not multiples of each other. Now let us multiply 2 and 5 with this one. We get 12 and 19, which lies somewhere here. I know these vectors are not drawn perfectly to scale, and they also might not show the exact directions, but that's totally okay. The point here is not to make an accurate geometric diagram, but to build a visual intuition. We just want to see what's going on. Now multiply -1, 2, and we get 3, 4, which will lie somewhere here. So this means that the outputs spread out across the plane. So, the matrix can reach any point in the 2D space. It's not restricted to just a line like before. Why? Because its columns are linearly independent. That means they point in different directions, and together they can cover the whole plane through linear combinations. So if you imagine all possible outputs you can get from this matrix, by plugging in every possible input vector, you'd get the entire 2D space. Thus, the column space of the matrix is all of R squared, which we write like this. So, it's not just a line anymore, it's the whole plane. Now consider this matrix. Look at its columns. Now tell me in the comments, what will be the column space of this matrix? Think about how the columns are related to each other. Are any of them multiples of the others? By the way, when it comes to finding the column space of a matrix, you'll often come across the row reduction method, and you'll find this approach online everywhere. However, I wasn't interested in just showing you the method. That's something you can easily look up. Instead, what I want to emphasize was the visual intuition behind it. If the column space concept is clear, then understanding the rank of a matrix will be a piece of cake for you. Rank is simply the number of linearly independent columns in the matrix, or in other words, how many directions in space the matrix can actually reach. In our first example, even though the matrix had 2 columns, they were pointing in the same direction. 1, 3, and the other column was just a multiple of the first column. That means the matrix could only reach points along a single line. So, the rank of this matrix is 1. But in the second matrix, the columns were not multiples of each other. They were independent, which means they pointed in different directions and could be combined to reach any point in the 2D space. Since there are 2 such independent columns, the rank of that matrix is 2. So you can think of rank as measuring the dimensions of the output space, which means the output vector can lie on a line, or 1D, so rank is 1, or on a plane which is 2D, or rank 2, or even higher. And yes, it can even lie on a single point, the origin, when the matrix sends every input to 0. In that case, the output space has no dimension at all, and the rank is 0. That's what happens, for example, with a 0 matrix, where no matter what input you give, the output is always just 0. Double noise! Let's talk about the next topic, which is null space of a matrix. Imagine this. You multiply any input vector with this matrix, do all the matrix multiplication, and the result is always just 0, 0, as if nothing happened. That collection of all such input vectors is what we call the null space. So while column space and rank is all about the output vector, the null space is all about the input vectors that go to 0, 0, or it simply becomes invisible after passing through the matrix. For example, consider this matrix A again. When we multiply any input vector x, y with it, we get this vector. But we need 0, 0 vector, and thus we equate this thing to 0, 0 to get this equation as 0, and this one also as 0. But the second equation is just 3 times the first one. Thus we only get x equals minus 2, y. So we can write input vector x and y as minus 2y and y. And by taking y common, we get y times minus 2, 1. That's it. This is the null space of matrix A. Minus 2, 1 lies somewhere here. So any vector that lies along this line, when multiplied with A, will always give us 0, 0. Now consider this matrix. When we multiply any input vector x, y with it, we get this vector. Equate this thing to 0, 0 to get this equation as 0, and this one also as 0. This gives x equals minus 2y. Substitute into this equation to get y equals 0, and thus x equals 0. So the null space contains only the 0 vector, which means the null space is just a single point, or the origin, that is, 0, 0. It's not a line, not a plane, just a tiny dot sitting at the center. Now what rank is for column space, the same is nullity of null space, which means the rank of a matrix shows the dimension of its column space, and the nullity shows the dimension of its null space. So, in this case, the nullity of this matrix is 1, and for this case, nullity is 0. Remember the rank of this matrix was 1? So, here's the cool part. If you add the rank and nullity for this matrix, you get 1 plus 1 or 2. Super cool! Now remember, the rank of this matrix was 2, so if you add the rank and nullity for this case, you will get 2 plus 0, which is 2 as well. And thus, no matter the matrix, rank plus nullity always equals the number of columns of the matrix. This is called the Rank-Nullity Theorem. So, for this case, we have the column space of this matrix as this, because the other two columns are just the multiple of this one, or they are linearly dependent upon this first column, and thus its rank is 1. Also, the number of columns in this matrix is 3. So, even without calculating the null space of this matrix, we can say that the nullity of this matrix will be 3 minus 1 or 2. By the way, using x, y, and z as the input vectors, can you find the null space of this matrix? And let me know your answer in the comments below. If this video gets 10,000 likes, then I will make another banger matrix video like this one. If you enjoy my videos and want to support my channel, consider becoming a Patreon, as it helps me create more awesome content for you. Link is in the description. Also, you can support my channel by joining our community and becoming a member. So, go